everybody! So today we're going to be looking at periodic trends that we notice on the periodic table and why we notice these different trends between atoms that we see on the periodic table. So I want to start with the question of what holds the subatomic particles together in an atom? Why are the electrons not flying away? What is holding this atom together? And we see that this, the reason is this force of attraction, which we call Coulombic attraction. And this is the attraction between positive charge and negative charge. Now we know that we have the positive protons in the nucleus, and we have the negative electrons out in the valence, or in the energy levels. So that attraction between the positives in the nucleus and the negatives in the energy levels are what hold the atom together. And this is going to be the reason for a lot of trends that we see, and they're going to be trends within families or periods. We also see that generally the trends within families are the result of what we call the shielding effect, and trends within periods across a row are what are a result of what we call effective nuclear charge. Now the shielding effect, the way to think of this is think of yourself at a concert. When you're especially if it's standing room only and you're all on the same level, if you're in the very back, you're being shielded from that stage and from the performer on stage by all those people in front of you. They are blocking your view. The same thing, same idea, is what we see with shielding effect in an atom. So as more energy levels are added to the atom, those core electrons actually shield or block the valence electrons from the positive nucleus. They're getting in the way of the valence electrons being attracted to that positive nucleus. We can see that with lithium and potassium. They're both alkali metals, but lithium has 2 energy levels, and potassium has 4. So lithium has much less shielding effect than potassium because potassium has all these core electrons that are getting in the way of this valence electron's pull to the positive nucleus. We also see the effective nuclear charge. This is within periods generally, and this is the pull that the valence electrons feel from the positive nucleus. Okay, so we know that the nucleus is positive. Here in lithium has 3 protons, whereas fluorine has 9 protons. 9 protons is a lot more, and so these have the same number of energy levels, but the 9 protons on fluorine are going to pull those valence electrons in stronger. Remember, protons are large, massive particles compared to electrons. So these more large, massive particles pull those electrons in tighter. Now, I'm not going to go into a ton of depth in explaining the trends that we see, except to say you're going to experience or use these when we're doing the activity in class to figure out why the trends are what they are. So let's take a look at 4 of the trends that we see. The first ones are atomic radius versus ionic radius. An atomic radius, when we say that, we mean the distance from the nucleus, from that center, to the valence energy level. Okay, so how far is that distance? And we saw something like this in our periodic table activity, but you can see we have these alkali metals over here are very large, the noble gases are smaller, and across the period we see that the size decreases as you go across the period. Okay, so that's what we see here. The size decreases across the period for an atom, and it increases down a family. We can also draw this on the periodic table. When we do this, we always draw it in increasing order. So the increase is coming to the left across the periodic table. Remember, any of the trends within periods is because of the effective nuclear charge. The increase down the group is because of shielding effect, right? And we're going to see that over and over again, okay? The other radius we can look at is the ionic radius, and this is the radius within an ion. So same thing, the distance between the nucleus to the valence, but specifically for the ion. And there's 2 types of ions we'll see. This one we saw in the flame test lab, and that's the cation. These are metals that lose electrons to become an ion, versus the anion, which is nonmetals, which will gain electrons to become ions, okay? So this is a general trend that we see. We have, for example, sodium and sodium's ion. Well, sodium has 3 energy levels. When it becomes an ion, it loses that 1 electron in its outer energy level, in its valence, and it becomes sodium plus with only 2 valence electrons. I don't know if you can see what I'm labeling them here. So this is sodium, and that's sodium plus. So 2 energy levels versus 3. Clearly, the atom here, right, is bigger than the cation, and that's what I have here. The radius of the atom is larger than its cation. Why? Because an energy level has been lost. In the anion, and I like to think of this as a negative ion, that's how you remember that it's the negative ion versus the positive ion. In an anion, we have, for example, here chlorine, Cl, versus its anion, Cl minus. They have the same number of valence electrons because chlorine has, or the same number of energy levels. Chlorine has 7 valence electrons. To become a noble gas and stable, it wants, or to become like a noble gas, I should say, with an outer valence full, it wants 1 more electron. So it gains that other electron, same number of energy levels, all that has changed is there's 1 extra valence electron. Well, what we see here is that the nuclear charge is not as strong with increased electrons. So the more electrons you add, that positive nucleus is not able to hold on to those electrons as tight. So the ion starts to get bigger, okay? So here, for the anion, the radius of the atom is smaller than its anion. The atom is bigger than its cation, and atom is smaller than its anion, right? Now, the last 2 trends that we're going to look at are ionization energy and electronegativity. Now, these, conveniently, have the same trend, right? So, let's look at the definitions. Ionization energy is the energy needed to remove an electron from an atom, okay? To take off 1 electron, just 1 electron from an atom. How much energy does that take? And it's going to take some amount of energy no matter what. And what we see is that going up and to the right across the periodic table, that ionization energy increases. So it is very, very difficult to remove an electron from this upper right-hand corner, which is helium, we have fluorine, we have neon, right? Those are very hard to remove an electron from. Why? Well, they're either noble gases where they already have a full valence and they don't want to lose electrons, or in the case of the halogens, right? Halogens are right here. They are very close to becoming the stability of a noble gas if they just gain 1 more electron. So they do not want to give up an electron for anything, okay? So the trend across the period, remember, always due to the effective nuclear charge. The trend up the family, always due to shielding effect, okay? Now the last trend we're looking at, electronegativity. This is kind of the opposite of ionization energy because this is the measure of an atom's attraction for another atom's electrons in a chemical bond. So, attraction for another atom's electrons, not its own, but how attracted it is to other electrons. Now, we also see the same exact trend, again, moving up the family because of shielding. That's the trend. This is the reason. Moving across, increasing across a period because of the effective nuclear charge, right? It's the same for all of them, the reasoning why, and we'll look into that more in class. But what we see is that over here, fluorine, it needs 1 more valence electron to feel like a noble gas. So it's going to be very attracted to another atom's electrons. It really wants another atom's electrons, right? The exception here is that the noble gases don't really have an electronegativity value because they are already stable, right? They don't want another atom's electrons. They have as many as they want, and they're stable as they are, okay? So these are the trends. We'll see in class a little bit about why the trends are.